So today we're talking about defeating signed BIOS enforcement, some exploits I found against the Intel chipset BIOS protection mechanisms and the BIOS update processes. And also, I didn't do this work by myself. I have some colleagues. We're part of a research group at the MITRE Corporation that works in low-level operating system and PC security. Okay, so first of all, I'm sure everyone already knows this. This is just reiterating a well-known point that BIOS rootkits are very powerful. They're the very first code that's executed on your computer, and because of that, if you have malware in your BIOS, it can subvert pretty much every other thing on your computer. So that's a desirable property for rootkits. The other thing that makes BIOS malware very desirable is it survives operating system reinstallations because the BIOS lives on a flash chip on your motherboard, right? And it doesn't go away if you just reinstall the operating system. It's just there kind of forever. Unfortunately or fortunately, we don't really see a lot of in-the-wild BIOS rootkits. Number one, because they're hard to implement. There's a lot of implementation difficulties associated with programming the BIOS. It's hard to debug, etc. Also, probably rootkits at this point don't really need to go to the BIOS level because you can still run amok in userland and nothing's going to stop you. So why increase the cost of your development if you're a malware developer if you can just do everything at the userland level? But perhaps as the operating system gets more locked down, if it ever does, or with new features like secure boot and so on, malware developers will eventually be forced to move deeper into the system to the BIOS level. So I think it's worth looking at. Okay, so despite BIOS security being an old topic, there's actually been a number of important results in the past 12 months or so. The first one was really Jonathan Broussard in Black Hat 2012 gave a talk about a BIOS rootkit he developed. And as I mentioned in the previous slide, previously people thought, well, BIOS rootkits aren't really an issue because implementation difficulties, and they're not portable between systems. And Jonathan showed, well, actually it's not very hard to develop a BIOS rootkit because you can pivot off of open source firmware projects like Open Firmware and so forth, and kind of use those as the underpinnings for your BIOS rootkit, and it makes things a lot easier and also makes your rootkit a lot more portable. So that was one result. Another one was basically Yuri at Black Hat this year, 2013, said, if you can get on the BIOS, you can defeat secure boot. And it's pretty obvious. The first code in the secure boot chain is on your BIOS. So if you can get onto the BIOS, this new Windows 8 secure boot feature, UEFIs, it's all defeated. And then the third important result that's really come out in the past 12 months is something I co-authored. That I'll be giving a short talk about this tomorrow, but the main points are that BIOS rootkits really are undetectable by conventional mechanisms. Even trusted platform module can't detect them. And BIOS rootkits are very hard to get rid of if you don't have physical access to the device, pretty much impossible, because the BIOS rootkit can develop itself in such a way that it will survive reflash attempts unless you're manually connecting to the flash chip with like electrical probes. You're not going to be able to get rid of it. I'll talk more about that tomorrow. Okay, so all of those results I just talked about assume that you can actually get onto the BIOS chip, that you can get arbitrary code onto the flash chip containing your firmware. As a side note, when I say BIOS, I mean UEFI and legacy BIOS. For this talk, they're really pretty much the same. So, as I mentioned, all the previous results assume you can get onto the BIOS chip. Obviously, vendors and Intel has grown aware of this possible issue. So, these days, most new systems are locked down where you can't get onto the BIOS chip. Theoretically, there are protection mechanisms. And the main policy is that only updates that are signed by your OEM can be written to your BIOS. And there's like a protection mechanism that tries to enforce that. That way you can't have any BIOS rootkits running around, because obviously they won't be signed with the private key from Dell or Hewlett-Packard or something like that. Okay, so how is this signed BIOS enforcement actually implemented? If we want to break this, we have to analyze the attack surface. So Intel, who provides the chipset on your motherboards, I'm talking PCs strictly here, they provide a number of protection mechanisms that they provide mechanisms to let you reflash your BIOS, and also protection mechanisms that try to control when and where you can do it and who can do it. And These protection mechanisms have stayed pretty much the same over the past several years, despite newer systems, newer Intel CPUs. These particular flash protection mechanisms really have remained pretty constant. Even new UEFI, the legacy BIOS, it's all built on these same protection mechanisms that we'll get into in a second. So it's up for your OEM, your Dell, or your Hewlett-Packard to use these Intel-provided mechanisms in an intelligent way to implement their secure BIOS update process and successfully do the signed BIOS enforcement. So obviously there's really two main attack avenues here. One is that the OEM has to implement this BIOS update routine, so perhaps we can find some memory corruption vulnerabilities in that. And also it turns out that the Intel BIOS protection mechanisms are quite more complicated than you would expect, so maybe we can find some attacks against those, and actually I'll show you an attack against each of those, and then also an unpatched vulnerability in like the latest, greatest UEFI systems. Okay, so protection mechanism number one from Intel that is supposed to protect your BIOS against arbitrary writes is something called the protected range registers, and this is all obviously this documentation freely provided by Intel. You can go to their website and look at your ICH, IO Controller Hub documentation, and look at this until your heart's content. Intel is very good at documentation, so it's very clear what's going on here. This mechanism is really quite simple. It allows you to define a range on the flash chip and then say, this range is not writable or not readable. So this is kind of the type of protection mechanism you would expect. Simple protection mechanisms are good. There's not a lot that can go wrong. So what would happen is the BIOS would configure this protected range register during each platform power on to lock down the BIOS against writes. And then to protect this particular register from being manipulated, there's the flash lockdown bit in this register, which once you set that bit, you can't make any more changes to the protected range registers. So theoretically, the BIOS would set the protected range registers and then set this, and then those things can't be modified until the system is reset again, so the BIOS will be completely locked down. Okay, so protected range register, simple, good. The other main protection mechanism we have, and also notice that these are duplicative protections. They can both protect your BIOS against writes. You could use one or the other or both and pretty much accomplish the same thing. This protection mechanism is pretty interesting. At first glance, it looks quite trivial. There's a bit that's BIOS write enable. If it's 0, you cannot write to the BIOS. You can only read to it. This is if you look at the RW in the Intel documentation there on the right, it means it's a writable bit, so you can't actually change this. But then they have this BIOS lock enable. And this is where it gets interesting. You would expect to see something like, once you set BIOS lock enable, you can no longer modify BIOS write enable. This is kind of the protection mechanism you would expect. But if you read the text carefully, you can see it's actually quite a bit more interesting than that. It's not really locking down the BIOS write enable bit. It just says, enable setting the BIOS write enable bit to cause SMIs, system management interrupts. Once set, this bit can only be cleared by a platform reset. So the BIOS lock enable bit isn't actually protecting the BIOS write enable bit. It's just setting up the system so that whenever the BIOS write enable bit is modified, system management mode will kick in, and then it's up for the OEM to implement a system management mode routine to jump in and actually protect the BIOS write enable bit. So it's up for the OEM to configure this correctly and then implement this SMN protection routine. So it's quite a strange protection mechanism in my opinion, and I'm not really sure why they did it this way. So I realize that's a bit unclear, so I just want to show you kind of an example of how this would work. So let's assume we have some ring 0 Windows kernel driver code that wants to set the BIOS write enable bit. That way it can write to the BIOS and install a super cool rootkit. So it says, okay, I'm going to set BIOS write enable to 1. This is all done with just PCI port I/O to the PCI configuration space. So any ring 0 code can do this. And in fact, in Linux, you can do this from userland if you have root access. And what happens is the second you set BIOS write enable to 1, it is actually kind of like 1 for a second, but as soon as that happens, system management mode kicks in, an SMI is generated, it goes to system management mode, which hopefully most of us know that's just like a hyper-privileged mode of execution in x86 that was traditionally used for important events like power management, thermal events, things of that nature. So SMM kicks in and it says, no, BIOS write enable stays 0, because I say it does, because you're not allowed to update the write enable bit. So presumably, maybe they did it this way so that system management mode could try to make a determination about whether or not the attempt to write enable the BIOS was legitimate or not, and then either allow or disallow based on that. But like I said, it's a pretty complicated protection mechanism. And whenever you see lots of text and sort of a confusing Intel protection mechanism in the data sheet, that's definitely the kind of thing you want to zero in on when you do this kind of work. So the end result is that if the OEM does this correctly, BIOS write enable will never really be set, so ring 0 code will never actually be able to change the BIOS. Okay, so this is just a little example on a Dell laptop. No attack occurring here, but I just wrote a little program. Like I said, in Linux, you can do this from userland as the root account. And this is just an application that attempts to set that BIOS write enable bit and then read it back. And you can see it's attempting to set the BIOS write enable bit, enable that lowest bit in the BIOS control register, which is the BIOS enable bit. But as soon as it reads it back, it's not set. You can see it goes from B to A, so it's actually cleared by system management mode. So the BIOS write enable bit does not stick, and the BIOS is never actually writable, because the system management mode is successfully protecting the BIOS in this particular instance. And you can use, there's actually a pretty useful Linux project, open source project called FlashROM. So if you're interested in this type of BIOS security, it's really good to look at their source code to see how you actually write to the BIOS and so forth, and look at all the protection mechanisms. And you can see if I try to do this from Linux here, just to try to write to the BIOS directly, you can see in the output there it's saying, trying to set the BIOS control register from A to B fails because system management mode is going in and preventing that BIOS write enable bit from being set. So since signed BIOS enforcement is enabled on this laptop I tried to do this on, we're not able to use FlashROM because the BIOS is locked down against arbitrary changes. Okay, so as I mentioned before, the protected range registers and BIOS control registers provide like duplicative protections of the BIOS. You could use one or the other, I guess it's kind of up to you however you want to try to protect your BIOS. As far as I know, Intel isn't really providing guidance on choosing one or the other. I'll get into some results about who is actually using one in a second. But the general thing is that these protections, they go to 0 when the computer is reset, and then it's up to the BIOS to correctly configure them each time the computer powers on. It's usually one of the first things that happens after it checks for a BIOS update or something like that.
Sorry?
Oh.
So you can choose what protection mechanism to use?
Yes. Yes, you could use either. It's really up to the OEM. Intel is just providing you these possible locks that you can use, and then Dell or HP or Lenovo, whoever is implementing the BIOS, can decide how they want to use those protection mechanisms to actually implement their BIOS protection and do their BIOS secure BIOS update.
This is just for UEFI or?
Legacy BIOS, UEFI, both. Anything that has like an Intel chipset, Intel I/O controller hub will use this. There are a few exceptions with like special server class machines. IBM's kind of doing their own weird thing, but all the consumer systems I've seen are doing it this way. Protected range registers, BIOS control registers, UEFI, legacy BIOS, it's all built on this technology, those protection mechanisms. Okay? Okay, so now that I've introduced the actual Intel protection mechanisms that are being used to do this, I want to show you guys how a vendor actually implements a secure BIOS update routine. That way we can start considering the attack surface on it. So the OEM is going to use those protection mechanisms, hopefully in an intelligent way, to only allow signed BIOS updates to be written to their flash chip. Okay, so basically I'll be showing you the BIOS update process for the Dell Latitude E6400, which is a sort of an older laptop. The only reason I am showing the E6400 is because it was compatible with our debugging hardware. If anyone's worked in BIOS or firmware, you'll know that getting debugging working is very difficult. So we chose the E6400 solely because it was compatible with our debugging hardware. But as you would expect, they basically share the BIOS update code all across most of their systems. So this update routine, even though the code I'm showing you is from an E6400 firmware dump, it's used by actually like 25 or 24 different other Dell models all across the board. Because if you think about it, it wouldn't be very cost effective to develop a new BIOS update routine for each new Dell Latitude that you put out. And I expect the update process among like Hewlett-Packard and other systems to be pretty similar as well. Okay, so the actual update process when you want to update your BIOS to a newer revision, you go to the OEM and you download the update image. In Dell's case, it's called the HDR image. And what happens is a Windows kernel driver takes that HDR image, the new BIOS update image, and it writes it into RAM. And then it flips a bit in CMOS to indicate to the BIOS that a BIOS update is pending and currently staged in RAM, and then the system reboots. And each time your computer turns on, it's going to check this CMOS bit, and if it's set, it's going to say, all right, I have a BIOS update pending. I need to go and look for my new BIOS HDR image somewhere in RAM. So it has to like scan all through RAM to locate this incoming image. And if there is no update image, if it detects, like most of the time when you're not doing a BIOS update, it says, okay, no incoming BIOS image, I'm just going to go ahead and lock down the BIOS because nothing is supposed to write to it past this point. I'm not going to do a BIOS update, so let's just lock it down and keep ourselves safe. That's how it's supposed to work anyway. One interesting thing that happens is your BIOS update image on newer systems is actually quite large. It can be like 10 megabytes, 16 megabytes, so the firmware is really pretty big. So the operating system kernel driver that stages this whole process will actually packetize the signed update image. That HDR image I just talked about has like a signature from Dell. And so the kernel driver splits it up into smaller packets and then spreads it all across the physical address space. So you end up with lots of different packets all over RAM. It tags these individual packets with like an ASCII string, and it puts them on page-aligned boundaries all through RAM. And then when the BIOS update process kicks off, this happens in system management mode, by the way, it's literally going to iterate through all of RAM, looking on these page-aligned boundaries for that RPK string to say, all right, where are my individual packets? And then it takes these individual packets and it reconstructs them into the HDR image. So that copyright 2011 Dell thing, that would be like your HDR image. That is what you started with in the operating system. It was split up into smaller chunks, and then during the update process, when your system is reset, it's going to find them and then reconstitute them into like a reconstruction space. All right. And the reason this is happening is because while you're running your operating system, there's less physical RAM available, less resources, since Windows is allocating lots of the RAM. So it's splitting them up into smaller pieces that can fit around. And then when the system is just reset, you have all of RAM available, and no one's using anything really. So it can just take that and then reconstruct it. And the important thing to notice here is that the signature check can only occur on the reconstructed image. Those individual packets are not signed by the OEM. It's up to the operating system to generate these individual packets on the fly based on the current resources available to the operating system. So it just generates these what's called RBU packets, these smaller packets on the fly. They're unsigned. It wraps them in some header information, and then the update routine locates all these packets, reconstructs the complete signed HDR image, and then the signature check occurs. So obviously, if you have worked in memory corruption vulnerabilities, you'll be thinking, well, I should look for bugs in the reconstruction process, because those individual packets are unsigned. And that's actually exactly what we're going to do. We need to find a memory corruption vulnerability in the BIOS update process. It has to occur before the signature check occurs, because the second they do that signature check, they're going to see this is a bogus BIOS image, done, give up, fail. And the method really is to find a memory corruption vulnerability in the scatter read and scatter write operations of the BIOS as it's reconstructing the signed HDR image from all the individual packets. So luckily for us, the system management mode update routine parses this header. All of those individual packets I was just describing are wrapped in this header. Delp freely provides this for some Linux libraries for some reason. And it's pretty much what you would expect for a software engineering problem of this nature. It contains things like sequence IDs, current packet size, number, etc., a checksum, and then obviously all the data is actually passing into that packet. So what you would expect, and it's just important to keep in mind that all of this data is completely unsigned because it's up to the operating system kernel driver to generate this on the fly based on the current resources available to the system. Okay, so let's get into the nitty-gritty of what one of these BIOS update routines actually looks like. Like I said before, this is happening in system management mode, that super privileged x86 mode. Whenever you see a DFF address in this IDA output, that means system management mode. It's the T-seg where system management mode lives on these modern systems. And the code we're looking at here, you can see the top line. This is the second an RBU packet has been located by finding that special ASCII string on page-line boundaries. And the first thing it does is take fields from that RBU packet header, and it copies them into a system management mode data area. That way it can use it for some calculations, kind of like a scratch space. And if you look closely, you can see that it's basically just copying these members directly to a data area, and not a lot of sanity checking is going on. There is a little bit, but I'll get more into that in a second. Okay, so as I was looking at this routine, I noticed something quite funny, actually. That the reconstruction space I showed you before, where the complete image is being reconstructed, during the update process, for Dell at least, while this is happening and while it calculates what the size you need for the reconstruction space, after it does all that, it writes this ASCII string all over the BIOS image reconstruction area, GEOR, and I assume it's because the guy that wrote this code was named George, and he was putting in like a debugging tag to kind of know where the reconstructed image should live, because if it's off a little bit, this kind of code would be very hard to debug running in system management mode. So I think it was just some weird debugging artifact that they left in there. The only reason I point this out is because it's going to come back to haunt us and make exploiting any vulnerabilities we find very difficult. Okay, so if we keep tracing through the BIOS update process, eventually we get to the code that's responsible for actually moving one of these individual discovered RBU packets into the reconstruction space. And this lower basic block here on the bottom right is what does it. And you can see that there's repmovesd inline memcopy. And if you look at the IDA output carefully, you can see that ECX, the size parameter for the memcopy, is derived from attacker-controlled data, which is just data from that RBU packet that was unsigned. So this is like a buffer overflow in system management mode. But it's actually quite a bit more interesting than that. For this particular vulnerability we discovered in the copying of these RBU packets, you don't just control the size parameter as you typically see in these buffer overflow scenarios. You also control or I shouldn't say control, you influence the destination, the source, and the size. So that is pretty interesting. It's not what you would usually see in finding vulnerabilities like this. And it actually, even though it gives us lots of options for what we can try to corrupt to exploit this update process, it makes things pretty, hairy as well, because if you can overwrite a whole lot, you can do damage to your system. This is in system management mode. you can break your system and things of that nature. It gets quite dangerous to play in this realm. So that overflow I showed you was in system management mode. The great thing is that system management mode has absolutely no exploit mitigations. There's no ASLR, no stack canaries. All the addresses are always the same. The only reason why system management mode would really change locations in the address space is if you installed or removed RAM in your system. So there's absolutely nothing to stop us from running a conventional exploit that like overwrites the return address or something like that. And it makes sense. The reason they don't do any of this stuff is because system management mode is supposed to execute and then finish very quickly, because like I said, it's supposed to handle thermal events and things like that. So they don't really have room for all this fluff. And like I said, system management mode is super privileged. They call it ring -2, below like the hypervisor and all that. So you can really pursue any target that you want to overwrite. You could try to overwrite your own code, and nothing is going to stop you. Okay, so we found that exploitable buffer overflow in the Dell BIOS update process. But exploiting it, like I said, was quite a bit tricky. And the reason is, I'm sorry, I should have added the structures into this IDA thing. I realize it's hideous to read. But what's underlined right there is the destination for the mem copy, the vulnerable mem copy with the overflow. And before it gets to this vulnerable mem copy, it checks to make sure that your destination points to this GOR string, that special debugging string that I told you about before. And if it doesn't, you're never going to get to the vulnerable mem copy. The reason why this is problematic is, I'll skip ahead to that slide to show you guys, that GOR string, that special debugging tag, does not actually occur in the address space when we exploit this. And that's because there is some limited sanity checking. You can see here it's making sure total data size is less than 8 megabytes. And to get around this, we basically just set the total packets, which is from that RBU packet information, to 1. Then total data size equals packet size times 0. The total data size is less than 8 megabytes. But then at this loop right here, it's not actually going to populate the GOR string through the address space. So that is an issue we're going to have to overcome, and I'll talk a little bit about how we did that in a second. Let me go back. Okay, so some other interesting constraints that made exploiting this pretty weird was that the way the exploit, the vulnerability is structured, you're going to end up overriding like many megabytes of physical RAM. And in system management mode, you can do that. And if you overwrite too much, you're going to like brick your system. Your system's just going to die, game over. If you overwrite too little, obviously you're not going to overwrite any function pointers. There's also special regions of memory that you can't touch, or else you definitely will die. So there's lots. We had to basically come up with a map of memory, being like, we can't touch this, we can't touch that, this is what we want to touch, and then figure out how to manipulate those source, destination, and size parameters for that vulnerable mem copy to overwrite what we cared about. Now, for this vulnerability, since, like I said, there's no special mitigations, we just chose to target a return address in system management mode that was in the context that we could overwrite to get control of the instruction pointer in the context of this update routine. And as I alluded to before, what made this kind of tricky as well was the destination, the source, and the size. We influence all of these, but they're all derived from the same parameters. So what this means is that if I want to change the size of my mem copy, that exploitable mem copy, it's actually going to change the source and destination as well. And likewise for the other parameters. So we have this mem copy, and it's letting us have like a sliding window in the address space of memory that we can corrupt. And we have to choose this window very carefully, because if we're over here, we break the system. If we're over here, nothing happens. So we have to like surgically choose how we choose these parameters so we get the sliding window right over the things we want to corrupt. Part of the way we exploited this, and this is kind of an interesting exploitation technique for vulnerabilities in this space, is that if you change things in RAM and do a soft reset of your system, like not pull the power plug, but just like tell it to reboot, most of RAM stays the same. It's not like your RAM is cleared out upon a platform reset. Most of it stays there for the most part. So what we did to exploit this was we wrote our Windows kernel driver to allocate as much physical memory as possible and kind of spray the address space with this GOR string, and also stage other things in memory that we needed. So it's kind of like a heap spray, except we're literally just spraying all over RAM. And we don't have to use any fancy JavaScript techniques or whatever to get things where they need to be. We can just program a Windows kernel driver and say, put this here, put this there, change 3 gigabytes of the address space, and then do a soft reboot. And most of them will still be there staged in memory while we're trying to exploit this. And like I said, we sprayed this special GOR debugging tag all over RAM. That way we could satisfy that one constraint and get to the vulnerable mem copy. And this mechanism where RAM stays the same is actually what the BIOS update process is using, that we're abusing. They're putting the BIOS update process in RAM and doing a soft reset. And because of that, the new update image is still going to be there in RAM as the BIOS is kicking off again, doing its update process. So with all those constraints in mind, I'd like to tell you that we use some amazing satisfiability solver or constraint solver, but literally I just programmed like for I equals 0 FFFF, for j equals 0 FFFF, et cetera, for all the possible BIOS update packet configurations. And I programmed in all those constraints just manually. And luckily, we found a special BIOS update packet that will allow us to overwrite some system management mode function pointers and not corrupt so much memory that we crash the system, and then eventually get control of the instruction pointer in the context of the update routine. So what this looks like, just to visualize, is normally we have, I'm sorry, it's a bit hard for you guys to see that color, but what this ends up looking like is we have one BIOS update packets with some very unusual parameters. So down here, I have the packet sequence number to like 83F9. Usually this would be like 1, 2, 3, or 4. And the size equal to FFFE, so very large. These are unusual parameters. And what this causes is it causes an overlap in the reconstruction space where the BIOS image is being reconstructed and system management mode RAM. And because this is all happening in the context of system management mode, we can do this without triggering any exceptions. And we can cause the reconstruction space to overlap with function pointers in system management mode and then get control of system management mode in the context of the update routine before any of those Intel locking protections mechanisms had been set. Okay, so I'll show you a little video of what that ends up looking like. Okay, so yeah, it's just Dell BIOS. This is my E6400, and what I'm doing now is just I'm going to go into the BIOS setup and show you that signed firmware updates are actually turned on. On most new systems, it's not even an option, it's just compulsory. You have to have signed firmware updates. So, oh, I missed it. Yeah, you can, if you look at your BIOS configuration, and if you have a new system, you'll probably see a line like this in your BIOS configuration that just says signed firmware update enable. And on most new systems, actually, it's not like you can just turn this off. Once you've turned on signed BIOS updates, it's there for good. Your BIOS is always going to remember that you're enforcing that policy, and you won't be able to get rid of it, even by downgrading your BIOS or something of that nature. It's with you for good, at least on most of the implementations I've seen. So what I'm doing now is I'm going to boot into the Windows operating system and use that kernel driver to spray the address space and stage in the malicious RBU packet into RAM. And then I'm going to sudo trigger the update process and hopefully exploit that vulnerability in system management mode. So what I'm doing here, that's just the Windows kernel driver, and we need it to be a kernel driver for Windows because you have to be a kernel driver to do port I/O to the PCI configuration space and memory mapped I/O. In Linux, it's not the case. You can do it from root. But that driver I just ran, it put the RBU packet in memory and then told the update process to kick off. And you can see that we have control of the instruction pointer in the context of the flash update program. And so from here, none of the protection mechanisms are set, and we can just reflash the BIOS with a rootkit or whatever we want to, despite the fact that there's this signed BIOS enforcement going on. So obviously I was just talking for a long time, and maybe you got bored about that. So exploiting the actual update process can be quite difficult. Just to give you some numbers, it took us, the hardest part about this was actually locating the BIOS update code. It took us literally 3 months, I'd say, of reverse engineering, like full time, to locate the BIOS update code. The reason is this was a legacy BIOS system, not UEFI. And with legacy BIOS, you never know where anything is. The actual update code was compressed with a special proprietary compression algorithm, so you would never see it if you just dumped the firmware. And so actually getting to it and locating it is an absolute nightmare. Once we had located the code, it took us a week to find the vulnerability and write the exploit. So it was difficult, but the main difficulty was just in reverse engineering the BIOS and actually locating the update, the relevant code. So yeah, just a conclusion of what I just showed you. We did report this to the vendor. Dell, I'll say, has been a great vendor to work with. We're working with their biosecurity team. They've been very responsive and helpful, so this isn't a knock on Dell. In general, I strongly suspect that other OEM implementations of update routines are going to have problems like this, because I've talked to some BIOS engineers and they admit that, you know what, we developed this BIOS update code before signed BIOS enforcement was even a consideration. Just 5 years ago, it was just given that if you had ring 0 access, you could reflash the BIOS. That wasn't even an attack. There was no attack surface. Yes, obviously you can change the BIOS. So this is a new consideration. What they're doing is taking their old BIOS update code and just bolting on a signature check. So when they developed this update code that does like BIOS update and scatter read and scatter write, they really weren't paying attention to buffer overflows and things of that nature. So I really expect there to be a lot of vulnerabilities in this space like the one we found. The main issue really is just actually getting to the code. So with that in mind, I told you we would also look at attacking the actual Intel protection mechanisms. So let's do that now. As I told you before, there have 2 Intel protection mechanisms, a simple one and a complicated one. The simple one is protected range registers. You just can't write to this particular part of the BIOS. And then you have the BIOS control registers. And so we're in the process of doing a survey of how vendors are using chipset configuration mechanisms to lock down their system. And right now we only have like 10, 20,000 data points, but hopefully we'll get to hundreds of thousands here in the next few months. And with our current data set, we found that 92% of systems, and take in mind that these are like systems that are 3 years old or newer, so relatively recent, 90% or newer that implement signed BIOS enforcement. So I'm totally discarding computers that don't even try to do signed BIOS enforcement. But 92% of those use only the BIOS control register and do not program the protected range registers. So this was kind of a surprising finding. I'm not really sure why that is the case, but it is definitely true. Yeah, just trying to speculate, I really don't even know why that would be the case. Perhaps BIOS control register is an older protection mechanism, so vendors have been using that longer, but I really don't know why that's the case. So since most vendors are only using the BIOS control register for BIOS protection, let's just only look at attacking that. And the main point is that BIOS control register, remember, is relying on system management mode to actually do the protection. It's just giving the OEM an opportunity to implement a system management mode routine that will protect the BIOS write enable bit. And this is a very bad entanglement in my opinion, because now the security of your BIOS is completely dependent on the security of system management mode RAM. And there have been many attacks against system management mode RAM. If someone can get into system management mode, then they can defeat your BIOS write enable bit protections and reflash your BIOS. And by the way, BIOS is responsible for instantiating system management mode. So once you get on BIOS, you control system management mode for life. Okay, so to illustrate why this is a problem, I want to revisit an old bug. In 2009, these guys, Rafal and Loic Deflo, co-founded a vulnerability that allowed them to get into system management mode, like on all Intel systems. And it's like a cache poisoning attack where they would pollute a CPU cache line associated with system management mode, then generate a system management mode interrupt. And at the time, they described it as a temporary attack on system management mode. You could get into system management mode RAM, but then once the system does a reset, system management mode will be wiped out, and the code you arbitrarily injected will be gone. But it turns out for 92% of those systems, we can pivot this into an arbitrary reflash to the BIOS, and thereby having a permanent presence in system management mode. Okay, so yeah, system management mode, it's very special. You can't read it or write it from outside of system management mode, even your Ring 0 driver code. The memory controller hub will block attempts to read or write to it. The key observation that those guys made was that you can change the caching policy for system management mode RAM to what's called write-back cacheable, which means it will like store the any changes you make in the cache in a special way. Let me just see the diagram. So you can change the cache policy of system management mode RAM to do something like this. You can pollute a cache line. It won't actually be written to RAM because that only happens in this caching scheme when that particular cache line is evicted from the cache. So the only time that the memory controller hub has to block your attempted access, invalid access to system management mode, is when that is written to RAM. So if this only exists in the cache, the memory controller hub will never have a chance to apply its protections and block you from doing this illegal write. So their attack was to pollute the cache line associated with system management mode and then generate an SMI. Arbitrarily, you can do that with special port I/O. And then all of a sudden, EIP, you get arbitrary code execution in the context of system management mode only because you polluted this cache line. And from there, you can do various things to change system management mode. Once you're in it, you can just do arbitrary changes to it. So this is a pretty cool, but actually rather simple attack on system management mode. And we can use this attack, which affects pretty much all PC systems 2009 and earlier, to transform it into an arbitrary flash to the BIOS. So what we're going to do is find the cache line associated with the BIOS, the system management mode protection of the BIOS write enable bit, and just change it to an RSM instruction, which is just a special system management mode instruction to just leave, don't do anything. And what this means is that system management mode will be called when we set the BIOS write enable bit, but it will never actually do anything to protect the BIOS write enable bit. And yeah, this is what ends up happening. As before, we have some malicious Ring 0 code in Windows, sets the BIOS write enable bit, and system management mode is canceled out, so this goes through perfectly fine. Going back to my Linux output, you can see, remember last time I tried to set the bit, and it read back as OXA, meaning that least significant bit was not set. And now if I try to use flash ROM to reflash the BIOS, despite the system having signed BIOS enforcement, it'll go through perfectly fine. And this is kind of cool because it affects, like I said, tons of older systems, pretty much all Intel systems like 2009 and before. So if you have like an old Linux system or old system in general and you want to play around with your BIOS, but unfortunately it's implementing signed BIOS enforcement, so you can't just easily do that, you could use this attack to reflash your BIOS quite easily. So even though this is an old vulnerability, it just helps highlight the fact that this BIOS control protection mechanism is quite fragile because it's depending on system management mode, the integrity of system management mode to protect your entire BIOS. So that bug I just showed you, I did report to CERT, and it was giving a tracking number, and I talked to vendors, and all the vendors I talked to basically said, we're not going to patch this. Obviously, they could fix the issue by implementing the protected range registers. But all the guys I talked to, the BIOS architects for various OEMs said, we're not going to bother to patch this in our old systems, which actually, in my opinion, is an acceptable response because it's not very cost-effective to have to keep doing BIOS updates for all these old legacy systems. So the good news for you hackers out there is that if you want to go after an old 2010, 2009, and before system, you basically have an easy way to get into the BIOS no matter what they're doing, unless you're using those protected range registers, which very few of them are. This bug was mostly patched, like I said, around 2009, 2010, by the introduction of the system management mode range registers, which specifically prevent this attack. The OEM, for the most parts, configure these correctly so that caching attacks on system management mode can occur. But just remember, BIOS control register is totally integral to system management mode RAM, and that is bad because it greatly expands the attack surface against your BIOS. So many of you are probably thinking, well, what about UEFI? Doesn't it solve all these issues? Absolutely not. Not at all. The underlying protection mechanisms are exactly the same, whether it's UEFI or legacy BIOS. It's still going to be using protected range registers or BIOS control registers because that's just what Intel provides. Vendors are still implementing their own BIOS update routine. It's not like Intel is giving you this is the firmware update routine. Everyone use this. There's only one body of code to audit. Still, it's the case that each vendor is kind of rolling their own. So that's obviously a case where you're going to have a lot of vulnerabilities. And the funny thing actually is that even new UEFI systems that are certified for Windows 8 and so forth are shipping with completely unlocked BIOSes. They don't use BIOS control. They don't use protected range at all. So it's technically part of the Windows 8 certification process, I believe, that your computer can only get the Windows 8 stamp if it has signed BIOS enforcement, but it's not the case. In our survey so far, we found that all ASUS systems are completely unlocked, even the brand new ones. Lenovo as well also has mostly unlocked systems. And in general, we're finding about 33% of systems in the past couple years during our survey have just completely unlocked BIOSes, aren't even bothering to do the signed BIOS enforcement, even though technically they're supposed to. So actually, despite UEFI, people saying, oh, it's more secure, it makes things much, much easier for an attacker, anyone that wants to get involved in this space. And let me show you why. So the thing that made BIOS very difficult, as I alluded to before, was that you have to go and locate the code that you're interested in, which is always compressed to some crazy proprietary format. With UEFI, everything is standardized. So you can use this handy-dandy tool, think you snare, EFI pwn, that will go and dump your EFI firmware volumes. It's all a standard structure. And it provides these nice ASCII tags. All of these are literally like PE executables you can just throw into IDA. So locating the code that you care about is all of a sudden orders of magnitude easier. You can see right there, the line my cursor on is Dell Flash Update DXE. So what took me 3 months before has now taken me 15 minutes. And now I have that update code. So I talk to people and they're like, well, we don't have to worry about BIOS anymore. UEFI is going to fix all those things. It's absolutely not the case. Don't believe that if anyone tells you. And the other funny thing is that system management mode is something that should be like deprecated because it's very old. It's overprivileged, in my opinion. It can be used to interfere with the hypervisor, with late launched VMs. So it's something they should be getting rid of. But the opposite is true. With UEFI firmware, vendors are pouring more and more code into system management mode. It's just getting bigger and bigger and bigger. So that attack surface against the BIOS control register is growing and growing and growing. For this particular system, it was a Dell Latitude E6430. There were 400 individual EFI executables. 100 of them approximately had the string SMM in them, which presumably means they contribute some code to system management mode. So the point is, these new UEFI systems have a huge body of code that lives in system management mode. An exploitable vulnerability in any of them can now be pivoted in those 92% of systems into a BIOS reflash vulnerability. Okay, so now I'm going to show you an unpatched vulnerability that is just in that light that I showed you with the problems of system management mode. Unfortunately, I can't really go into the details of what we're doing because This affects a lot of vendors, like many new vendors that have Windows 8 Secure Boot, etc. And it's going to take them a while to patch it. And I would just love to give you guys unpatched vulnerabilities, but this is the time of year in my company where I ask for my annual raise. And if I give you the vulnerability, my managers will say, no, Corey, that's very bad. Your raise sucks this year. So I'm going to, I'll be happy with their wishes, and yeah, but I will show it to you. And I think if you read my slides closely, you'll kind of be able to tell what's going on. System management mode has a lot of problems, and if you can get into system management mode, you can reflash the BIOS. Okay, I realize I should have provided more contextual information for this demonstration, but what's going on is this is like one of the latest, greatest Dell systems running the latest, greatest UEFI firmware. And once again, it's relying solely on the BIOS control register to protect its BIOS. And down here, this is the bit, OXA, that is the BIOS control register. And so that's what should be being protected, and that's the sole register that's protecting the BIOS right now. And what's happening now is I'm going to try to flip that least significant bit. Right now I haven't done anything. So you'll see it immediately goes back to OXA. The bit did not stick. System management mode is protecting that bit. The only reason you saw any delay there in a second is because this tool I'm using has a slower refresh rate, but in actuality it was instantly reset by system management mode. And what I'm going to do now is install a super secret Windows kernel driver, which is going to mess with system management mode. Yeah, and then the least significant bit is set. And system management mode at this point has been completely lobotomized, and we can do anything. And we could reflash the BIOS, do anything we wanted to. And as you'll see in my talk, tomorrow, once you're on the BIOS, you can do all kinds of crazy things. So the point is, relying on system management mode for the protection of your BIOS chip is a very bad entanglement, and Intel needs to do something to force vendors to start using the protected range registers, which are a much better protection option. And like I said, we've reported this to CERT, but it's going to be many months before this is actually patched by the vendors because of the nature of the problem. And with this, you could defeat secure boot and all kinds of other stuff. It's once you're on the BIOS, you can do all kinds of crazy stuff. So yeah, in conclusion, vendors should be using protected range registers, but for the most part, they are not. Sole reliance on this BIOS control protection mechanism has dangerously entangled the security of your BIOS with the security of system management mode RAM. There's going to be lots of vulnerabilities in your OEM firmware update processes. You can exploit any of those to reflash the BIOS. That's even if they're using the protected range registers. If you exploit the update process, you can get on the BIOS. And any vulnerabilities in system management mode can be pivoted on those systems to reflash vulnerabilities. And these issues are completely UEFI BIOS agnostic. UEFI is not fixing any of them, besides to say more often you should be doing signed BIOS enforcement, but that's really all you're getting out of there. It's like I said, as I showed you, it makes reverse engineering orders of magnitude easier. And yeah, like I said, even new UEFI systems that are shipping are not even bothering to use these protection mechanisms. You could just reflash the BIOS and beat secure boot and write a super cool BIOS rootkit if you really wanted to. So that was my talk about how to break that particular access control mechanism to get onto the BIOS. And then tomorrow I'll be giving a shorter talk, 25-minute talk about some of the things you can do while you're actually on the BIOS. So thank you for listening.